In this lesson, we're going to take a look at IP headers. IP headers are really important because they tell us a lot of information about what's going on with the datagram that's on the network, where it's going and how it's going to get there, and a lot of other information. So let's just take a quick look through the IP headers and see what we can find. So I've got a Wireshark capture here, and this capture just has a number of, in this case, they're ICMP messages, which are, of course, IP packets. So I've got the IP portion of the packet open here. And I could close it up and you could see that I've got my layer 2 header, and then I've got my layer 3 header, and then here's the payload, which is ICMP. So I'm going to open up the IP header portion. Just scroll down here so you can see the entire thing. One thing about Wireshark I just want to point out here, when you select different portions, it actually shows you in the lower part where in the raw message that particular section is located. You see, when I've selected version, it actually has highlighted 1 byte out of the raw data down at the bottom where it's pulled that version from. You can see also that in addition to the version, I get the header length. Those two things are combined in that 1 byte. And in this case, you can see the header length is 20 bytes. That tells me that this entire header here, the entire IP header, is 20 bytes. So I've got 20 bytes that has my IP header in it. So that's the header length. Moving down, the next portion is the differentiated services field, or diffserv, and that's sometimes used for type of service, or TOS. Typically, what this is really used for is quality of service. So I can differentiate my types of traffic so that more important traffic gets a higher priority. And what this really is all about prioritization, so that you can make sure that the things that are really reliant on being there on time, so voice and video are good examples of this. And gaming traffic sometimes, although most network providers probably won't prioritize gaming traffic, but certainly voice and video will get prioritized because they're really sensitive in terms of the time it takes for a message to get from one endpoint to another endpoint. So we would use this differentiated services field, or diffserv field, to flag them as either voice or video so that our provider can prioritize that traffic and make sure that it gets to the other end faster. Now, I've got the total length, and that's the total length of the packet here. That includes the headers as well as the data. You can see that's 100 bytes. I've got my IP identification field here, or IP ID, and that identifies fragments of datagrams. So if I have to split a message up and I'm going to create fragments, I need to be able to put those fragments back together. The IP ID will actually help me do that. So I've got an identification header here as well. Now I've got a few flags, and we were just talking about fragmentation. So different networks actually have maximum transmission units. So for example, Ethernet, typically the maximum transmission unit, meaning the largest size chunk of data that it can take across the physical medium, is 1500 bytes. That's pretty typical for Ethernet. You get 1500 bytes to send in any particular packet. So if you've got data that is more than 1500 bytes, then you're actually going to have to fragment the data up into multiple packets. So I've got a more fragments bit here to indicate that I've actually got more fragments or more portions of the data that are going to come. I've also got a don't fragment bit. What that says is don't actually chunk this up. Sometimes that will cause messages to be dropped, because if you say you can't fragment it and we hit a portion of the network where the maximum transmission unit, or the MTU, is actually smaller than the amount of data that you've got and it needs to be fragmented, but you've got the don't fragment bit set, then the message is probably just going to get dropped. Then I've got my fragment offset, tells me where in the stream of data this particular fragment is going to be. I've got a time to live header. Now, in the protocol specification, it actually specifies that the time to live is in seconds, but in practice, this is really a hop count field. The number of network devices you go through are called hops. So every time I go past a network boundary, which is handled by a router, then I've gone a hop. As I said, in practice, we actually keep track of hop counts. So we keep track of the number of routers that we go through, and that's our hop count. This time to live, in this case, 255, it would be unusual for you to go through 255 routers to get from one place to another. But let's say you had your TTL set to 10, for example. Once you hit a device past that 10, then the packet's just going to get discarded because you've exceeded your time to live. And actually what would happen is we'd send a message back as an error back to the sending host saying packet expired in transit or message expired in transit. So for every router that this passes through, this time to live field here would get decremented. So we'd subtract 1 from it. And once we hit 0, now we've expired in transit and we've got to do something, which would probably mean that we're going to generate an error. Now I get the protocol field here, and the protocol just says which IP protocol is going to be transmitted as the payload or the data that's part of this IP message or this IP packet. I've got ICMP here in this case, and you can see it's actually protocol 1. And if I look down at the bottom here, you can see it's 01, and that actually is where we get the 1 from. So there's a whole byte that's used for this protocol field here. Now, I've also got the header checksum, and it says 929B, so that's 2 bytes that are used for the header checksum. And you can see here the 2 bytes that get used for that header checksum are right here. So 929B, and the header checksum is just there to make sure that the data hasn't been altered in some way. So we want to make sure that the data that was sent matches the data that was received. So both ends would perform a checksum. It's just a mathematical computation. And assuming the checksums match, we can make sure that the data that was sent is more than likely the data that was received. So that's what the checksum is there for. And this is really just the checksum on the header. It's not actually the checksum on the data. So we know the header hasn't been altered in some way through some sort of man-in-the-middle attack or something like that. Then I've got the source IP address, and you can see down here there are the 4 octets that are the source IP address. And I'm going to click on the destination. I've got the 4 octets here that are the destination IP address. And by octet, I mean a collection of 8 bits. Each section of an IP address is actually 8 bits, and we'll talk about addressing in a different lesson. But just so you know, each of these between the dots is represented by 8 bits, which means we can have values from 0 to 255. I've got 1 byte, 2 bytes, 3 bytes, and 4 bytes there. Those are my 4 octets. Same thing here, 1 byte, 2 bytes, 3 bytes, and 4 bytes. And then down at the bottom where it's highlighted in the raw message, you can see the 4 bytes there as well. So that's really the IP headers in a nutshell and what the different sections mean, and the different pieces of data that you can find in the different headers and how they're all used. So that's the IP header in a nutshell.